Today I'll be talking about graph theory, but these graphs are not the curves like y equals x cubed that you see in maths books, but are diagrams that depict connections between things, such as the London Underground network of stations linked by rails, or chemical molecules, as shown here, with carbons and hydrogen atoms linked by chemical bonds. The nature of the connections doesn't matter. For example, the underground map doesn't show the lengths of the connecting rails, or whether they're curved or straight. All that matters is which stations are connected to which. It's exactly 50 years this year since I became interested in the history of graph theory, which is what I'll be talking about today. In the 1970s, I collaborated on the book on the left, Graph Theory 1736 to 1936, not a very exciting title, in which we presented the subject's first 2 centuries by means of a number of original articles translated into English where necessary. Then, earlier this year, Princeton University Press published Graph Theory in America. This arose out of the doctoral thesis of an Open University student of mine and describes in particular the American aspects of the story between 1876 and 1976, but we do include all the European work as well as that. And just last week, I and 2 colleagues from America and Denmark submitted the manuscript on the right, which presents the 20th century story up to the present day. So today's lecture is partly a book launch past, present, and future. So how did graph theory arise? As the preface of our first book observed, the origins of graph theory are humble, even frivolous. Whereas many branches of mathematics were motivated by fundamental problems of calculation, motion, and measurement, the problems which led to the development of graph theory were often little more than puzzles, designed to test the ingenuity rather than to stimulate the imagination. But despite the apparent triviality of such puzzles, they captured the interest of mathematicians, with the result that graph theory has become a subject rich in theoretical results of a surprising variety and depth. And indeed, graph theory today pervades every area that involves connections. Road, rail, and communication networks, operations research, neural nets, computing, social networks, chemistry, and much else besides. So because graph theory arose out of puzzles, largely, today I'm going to focus on 6 of these historic puzzles, describing how they arose, bringing their stories up to date, and introducing you to some of the major problems with which graph theorists are involved. Some of these will be familiar to you. There's the Königsberg Bridges problem, the Knight's Tour problem in chess, the utilities or gas, water, and electricity problem, a problem arising from goodwill hunting, the minimum connector problem, and the map color problems. But first, let me introduce some terminology which I'll need, most of which is pretty straightforward. So in this talk, a graph consists of some points, usually called vertices or nodes, which are joined in pairs by lines called edges or arcs. So on the left is a graph with 5 vertices, joined by 7 edges. If all the vertices are joined, we have a complete graph. So such as the second one, which is the complete graph K5. For any vertex, the number of emerging edges is its degree. So the first graph has 2 vertices of degree 2, that one and that one. It has 2 vertices of degree 3, this one and that one, and a vertex of degree 4. And if all the degrees are the same, the graph is called regular. So the complete graph K5 is a regular graph of degree 4. There are 4 edges out of each vertex. The third graph is also regular, this time of degree 3, and we sometimes call it a cubic graph. Most of the graphs have cycles where you go around and return to your starting point. So you can see in the first graph, for example, there are 3 triangles, a couple of quadrilaterals, there's one, there's another one, and the outside pentagon. But a graph with no cycles is called a tree, like a family tree. So on the right, the graph on the right is a tree which is well known for its bark. I've been telling that joke for 50 years. Finally, a bipartite graph is a graph in which every cycle has an even number of edges. For example, the third graph there is bipartite because you can see some quadrilaterals, you can see some hexagons, like this one here, and the outside octagon, of course. But there are no triangles or pentagons, for example. And notice that the tree is also a bipartite graph, because all the cycles there, well, it has no cycles at all, let alone odd ones. So let's now return to the problems. The first of these is well known, I'm sure, to many of you, and concerns the medieval city of Königsberg, now known as Kaliningrad. As you can see, there are 4 parts of the city, 1, 2, 3, 4, joined by, all connected by 7 bridges. And the problem that the citizens had was to find a walk which crosses all 7 bridges once only, and if possible ends up where we started. So you could start here, up, and then down here, and then there, and then there. Whoops, I've left out that one. So let's start with that one here. Oh, I've left out that one. So it's not awfully easy to do that. And in fact, the citizens soon found themselves unable to do so, but is this really the case, or is there such a route? And at this stage, we welcome Leonhard Euler, the most prolific mathematician of all time, who has actually lectured here at Gresham College in a certain period costume. He solved the problem introducing his published solution with the following words. In addition to that branch of geometry which is concerned with magnitudes, there's another branch, previously almost unknown, which Leibniz first mentioned, calling it the geometry of position. This is concerned only with the determination of position and its properties. It does not involve measurements, nor calculations made with them. It hasn't yet been satisfactorily determined what problems are relevant to this geometry, or what methods should be used in solving them. So when a problem was recently mentioned, I had no doubt that it was concerned with the geometry of position. So it's a geometrical problem, but one which doesn't involve any ideas of measurement or length or angle or anything like that. So, and the problem he's referring to, of course, is the Königsberg problem. So how did Euler solve it? So he first redrew the map of Königsberg, as you can see up here, to show the connections more clearly. And you notice that all ideas of distance have now gone. The important thing is the connection between the 4 land areas and the connections formed by the 7 bridges. And he then used a counting argument. For a successful walk, whenever you enter a region, you must be able to leave it, which means that you use 2 bridges. So the total number of bridges around each region must be a sum of 2s. That is an even number. But here the number of bridges around each area are 5, 3, 3, and 3. 5 around region A, 3 for B, 3 for C, and 3 for D. And these numbers are all odd, so the walk cannot be done. The Königsberg bridges problem has no solution. But actually, if exactly 2 of the numbers had turned out to be odd, then we can still solve the problem as long as we start in one of the odd regions and end in the other. And Euler illustrated this in this example below. This also appears in his paper of 1736. He illustrated this, and here the number of bridges around the areas are, for A, you've got 8. For B and C, you've got 4. 3 for D, 5 for E, and 6 for F. And so you can complete a walk as long as you start and end in the regions D. So if you want to go over each of the bridges, you start here, and then you can cross all of them and end up there, or the other way around. Well, what has all this to do with graphs? Well, the way we solve such problems now is to draw a graph whose vertices correspond to the regions, whose edges correspond to the bridges, and where the number of bridges around a region becomes the degree of the corresponding vertex. The problem is then to, and so you get the picture down below. The problem is then to draw the graph in one continuous pen stroke, so you've got to draw the graph without repeating any line. And the condition for solution is now that the number of vertices of odd degree is either 0, in which case you end up where you started, or 2, in which case you start in one odd degree and end in the other. So for the Königsberg problem, we get this graph here, and the degrees are again 5, 5, 5, 3, 3, 3, which are all odd. There are 4 of them, so there's no solution. Now, regrettably, it's often claimed that this was how Euler originally solved the problem. Even just a couple of months ago, I saw an article which said that Euler solved the Königsberg problem by drawing the graph. He did not draw that graph. And as far as I can find out, the earliest appearance of this Königsberg graph seems to have been in a popular book of mathematical recreations written as late as 1892, more than 150 years after Euler originally solved the problem. And indeed, when the Quadrennial International Congress of Mathematicians was held in 2014 in Korea, the Congress issued this postage stamp of the Königsberg, the Königsberg map, with the graph. And it says at the top, Leonhard Euler. This was the International Congress of Mathematicians, and they got their history completely wrong. What a shame they never read our books. But such diagram tracing puzzles became quite popular in the 19th century, and here are 3 examples. We can certainly trace the first one in one continuous pen stroke because the vertex degrees are all even. They're all 6. And one way is go around the outside, then jump one each time, 0, 2, 4, 6, 1, 3, 5, 0, and then jump 2 at a time, and so on. And so that's one way of doing that. For the picture on the right, can you draw that in one continuous stroke? Or 2? Or 3? If you count the number of vertices of odd degree, you'll see there are 8 of them. There are 8 vertices of degree 3. Now, each walk will take up 2 of them, so it means you're going to need at least 4 walks. And then you find you can do it with 4. You start here, go all the way around, and then you add these 3 separate ones. So 4 is the answer to that question. How about the lower one? This is a nice picture. It was introduced in 1847 by Johann Benedict Listing. He was a mathematician particularly interested in the mathematics of optics. And he was the person to introduce the word topology to mathematics. Topology is often described as rubber sheet geometry. If you draw a picture on a bit of rubber and you stretch it, of course, you lose all ideas of length and angle and everything. But some properties are still preserved. And what properties are preserved, that's what the subject of topology is all about. And it was Listing who introduced that word, first of all in a letter he wrote in 1838, and then in an article he wrote in 1847, where he presented the last 2 of these diagram tracing puzzles, and pointed out that this you can do in one continuous stroke. You can do it in one pen stroke because this has got degree 5, that's got degree 5, all the others have got even degree. So you know that you can do it as long as you start at one end and end at the other. It doesn't tell you how to do it, but you know that it can be done. Let's now turn to our second problem, known to chess enthusiasts as the Knight's Tour problem. And this problem, many centuries old, asks whether a knight can visit all the 64 squares of a chessboard by knight's moves and return to its starting point. And knight's moves, you can recall that a knight always moves 2 squares in one direction and 1 square in a perpendicular direction, so it can go to any of the squares marked here, 2 in one direction and 1 in a perpendicular direction. Well, before embarking on that problem in generality, let's see what it entails and its link with graph theory. And so I'm going to look at the simpler example of a 4x4 chessboard, the one down here. First of all, you can draw a graph with 16 vertices, with the vertices corresponding to squares of the chessboard. And the edges correspond to knight's moves. So there is a link with graph theory. And the idea is you've got to trace this whole picture passing through every vertex. So our problem in this case is to find a cyclic tour which visits each vertex exactly once and returns to the start. But this is impossible because if you, to pick up this vertex, you're going to need to have these 2 edges. To pick up this one, you're going to need to have these 2 edges. And that already completes a cycle, and so you've left out a whole lot of the squares, so you're stuck. And similarly for a 5x5 one, to pick up all these 4 corners here, you're going to have to include these edges, these ones, and these ones. And so already you've completed your cycle, and there's still a lot of squares you haven't visited. So that one doesn't work either. But for the 5x5, in fact, there's an even simpler way of seeing that you can't do it, because a knight always moves from a black square to a white square, or a white square to a black square. And so any cyclic path must alternate black, white, black, white, black, white all the way around. And what does that mean? That tells you that the number of black squares must be the same as the number of white squares. But if the number of black squares and white squares are the same, that's impossible when there are 25 squares altogether. And so similarly, there are no knight's tours on a 7x7 chessboard, or a 9x9 one, or for any chessboard with an odd number of squares. So turning now back to the original 8x8 chessboard, we meet Euler again. Euler seems to have been the first mathematician to study the problem mathematically. There were 2 papers that came out around that time. Euler wrote one in 1759, and there's another paper by someone called Vandermonde, who's known in mathematics for something called the Vandermonde determinant. Vandermonde wrote 6 papers, none of which mentions anything about the so-called Vandermonde determinant, but there we are. But Euler got interested, and he studied the problem. And first of all, he came up with this solution, 1, 2, 3, 4. The trouble is that 1 and 64 don't match up. But he did actually work a bit harder, and he did find some solutions to this problem. And here's a solution. This is a particularly interesting one. Here you can see the knight starts here and goes around here. And if you count the squares as you go, 1 to 2 to 3 to 4 to 5 and so on, then you get this pattern of numbers here. And what's interesting about this particular pattern of numbers is not only does it give you a knight's tour, but it's actually what we call a semi-magic square, because if you add up all the numbers in each row, you get 260. And if you add up all the numbers in each column, you get 260. Now, if it were a real magic square, if you added all the numbers on 2 diagonals, then that would also be 260, and it's not. And so the question is there a solution where you can actually get the diagonals adding up as well? And it was only very recently, I think, that there's a computer search which showed that unfortunately, there is no solution where you can get the diagonals working as well. But even so, that's pretty remarkable, I think. And on the top right, you can see Euler's solution for a 10x10 chessboard with the numbers from 1 to 100, all linked up by knight's moves. Again, 1, 2, 3, 4, and so on. Well, these problems of visiting all the vertices crop up in different situations. Some years ago, a Cambridge scholarship question began with the words, "An intelligent fly wishes to visit all the 6 corners of a cube." Anything more stupid for a fly to wish to do seems hard to imagine. But anyway, so here's a cube. Now, you can actually draw the graph of it. If you sort of flatten it, you get this picture here. And so where does the fly go? The fly starts here and goes around there. And so on. I once gave this lecture using an overhead projector, actually. And unknown to... I couldn't see it, but the audience could, and there was a fly there. And just when it started walking along the path. And so the audience were in fits of laughter, and I didn't know why. But they were. So that is how you do it for a cube. So the solid lines gives us a route the fly can take, but unlike the bridges problem, where we go over every edge, inevitably passing through some vertices several times, here we're visiting every vertex just once, inevitably omitting some edges, the dashed ones there. So it's like the difference between an explorer who explores every path and a traveller who wishes to visit every city. And we can ask the same question of other polyhedral shapes as well. The second one is an octahedron, 8 faces, and if you squash it flat, you get this picture here. And it's quite easy to see, to find a path which goes through all the vertices. And we can ask the same question also for a dodecahedron. The dodecahedron's got 12 pentagonal faces, and if you squash it flat, you get this picture, and the red path tells you gives you a path through all the vertices. And that's a particularly interesting one historically. Because in the 1850s, in connection with some researchers in algebra, the Irish mathematician Sir William Rowan Hamilton asked for such routes on a dodecahedron, subject to certain conditions. For example, can you find, you can easily trace this, you just follow the consonants B, C, D, F, G, and so on. But supposing you're told that you have to start J, E, L, D, B, how many ways can you complete it? There are a number of questions that he posed there, which he found quite fun. And in fact, so much fun he found it that he turned the problem into a game called the Icosian game, where the 20 vertices correspond to the 20 consonants of the alphabet. And we seek a voyage round the world. So if you start B, C, and so on, B was Brussels, C was Canton, and the idea is to get to Z, which was Zanzibar. And he sold this game to a games manufacturer for £25, which was a wise move as it didn't sell. I once went to the Irish Academy where they actually have an original. They're all solid ones, but the best ones are the flat ones here. And I went in, and there are lots of people there studying 6th century Irish manuscripts. Some of them looked as though they'd been there since the 6th century. And there I was with all my pegs putting things in, having great fun, getting some very funny looks. Now, because of Hamilton's fame and influence, graphs which have a route through all the vertices are now called Hamiltonian. But they should really be named after the Reverend Thomas Pennington Kirkman, a Lancashire country vicar whose parish duties left him lots of time for mathematics. He became a Fellow of the Royal Society, and he also had 7 children. For Kirkman was writing about cycles on polyhedra in general before Hamilton did, as I say, not only for a dodecahedron. So Kirkman was there about 6 months before Hamilton and more generality, but Hamilton is so famous that they're now still named Hamiltonian instead of named after Kirkman. But Kirkman also gave examples of polyhedra which don't have any such cycles, such as the one here. And his paper on this one here starts off, if we cut in 2 the cell of a bee, then you get this particular pattern here, which I'm prepared to believe. To see why it has no Hamiltonian cycle, we notice that the graph is bipartite. All of the cycles have even length, which means that we can colour its vertices red and blue so that each edge has a red end and a blue end, which I've done here. So I've covered each each edge has a red end and a blue end. And now we have the same example that we had before, because any cycle must alternate red, blue, red, blue, red, blue, and so on. So there must be the same number of vertices of each color. But there are 6 red vertices there and 7 blue ones, so no cycle can be found. So as I said, that's somewhat similar to the argument we used for the 5x5 chessboard. So talking about Hamiltonian graphs before moving on, let me conclude with a slightly more recent result. Because in 1880, the question had been raised as to whether every cubic polyhedron, that's one with 3 faces meeting at each vertex, each corner, whether every cubic polyhedron has a Hamiltonian cycle, as does the cube and as does the dodecahedron. Well, Kirkman thought about this in 1884 and couldn't decide whether it does or not, saying it mocks alike at doubt and proof. So that didn't help much. And it actually took over 60 years before the problem was finally settled by Bill Tutt, who is a major figure in this country's history. In Bletchley Park, he was mainly the person who decoded the Hitler's tunny codes at Bletchley Park, but he later became a major figure in graph theory. And in 1946, Tutt wrote a paper which actually follows from some of the graph theories he was doing at Bletchley Park. He published an example of this polyhedron here. If you think of wrapping it round, you actually get a polyhedron there. That's the flattened version. And that's got 46 vertices, and it has no Hamiltonian cycle. So after all that time, he found a counterexample. He answered the question with the answer no. And since then, a few other examples have been, some smaller examples have been discovered. So moving on to our third problem, it arises from a utilities problem in which 3 unfriendly neighbours, A, B, and C, whom I usually call Mr. Angry, Mr. Beastly, and Mr. Cross, they wish to connect their houses to the 3 utilities of gas, water, and electricity in such a way, because they're unfriendly, that none of the connections must cross. Now, the origins of the problem aren't known, although it was certainly presented by the American puzzler Sam Lloyd, who wrote puzzle books in America around 1900. And on the right is an attempted solution where I've tried to insert the nine links. So here you can see them, except I haven't linked B to water. So how do can I put the 9th one in? Or can I rearrange it so you can do the 9th one? And so that's a big question. Can you draw the 3 utilities, 3 houses, can you link them up with 9 edges? So in graph theory, in graph theory terms, we've got this picture here, and we want to redraw this so that none of the edges cross. Okay? And so what we're asking, a graph is planar if you can draw it in the plane without any crossings. So the question is this planar? So nothing could be much plainer than that. So we can ask this question, and the answer is no, to see why. You notice that 6 of them form a hexagon. You can go G, B, W, C, E, A, and back to G. So you can draw those as a hexagon, and then you've still got the other 3 edges to fit in. So let's take this horizontal one. If that goes inside, then both of these must go outside so they don't cross it, but then they'll cross each other. So that's no good. And if you put this one outside, then these 2 will have to be inside, but they'll still cross. So in either way, there's no way of doing it. The graph cannot be drawn in the graph, cannot be drawn in the plane, and the utilities problem has no solution. So when, in general, is a given graph planar? And this was answered, actually, by several people at the same time, but the important person I want to mention is a famous Polish topologist called Kuratowski, whom I met once, actually. It was very interesting. So some graphs, such as the such as this. These are planar because you can redraw it. You can pull these things out, and that's planar. But this one is not planar, and in the same way, you can show that this one is not planar. That's quite an easy thing to do as well. So these two are not planar. The important result of Kuratowski is these are essentially the only ones. Because if you have a graph which is not planar, then it must contain at least one of these two. And that's quite a remarkable result. Interestingly, Kuratowski himself said that he was assuming that was the only one that didn't work, and it was only when he came to the end of the proof that suddenly popped up. So he had to deal with that as well. But that's a very famous result in graph theory, which describes completely when a graph is planar or not. These are the only obstacles. But we can say more about planar graphs, and this is Euler again. In 1750, Euler observed that for any polyhedron, the number of faces plus the number of vertices is the number of edges plus 2. For example, this has 6 faces, 8 vertices, 12 edges, and 6 plus 8 is 12 plus 2. For a dodecahedron, there are 12 faces, there are 20 vertices, as we saw, 30 edges, 12 plus 20 is 30 plus 2. And here's a great rhombicosidodecahedron, as it's called in the trade, and you can see immediately that it has 62 faces, 120 vertices, and 180 edges, and 62 plus 120 is 180 plus 2. So it doesn't have to be regular. You can have different types of faces, and the result still works. So this is an important result. How did it arise? Well, let me show you the place it first appeared. Euler had been in St. Petersburg for a time. He then moved to Berlin in 1741, and in 1750 he wrote to his friend and colleague Christian Goldbach, who was still in St. Petersburg, and who is famous for an unproved conjecture on prime numbers. Some of you will know of Goldbach's conjecture. And the formula, Euler's formula, is right here. H plus S equals A plus 2. Here H is hedrai, Latin. Hedrai, Latin for faces. S talks about solid angles. The solid angle is, if you like, a vertex. And A is achies, which is an edge. Interestingly, Euler was, lots of people had looked at polyhedra in the past. The ancient Greeks had, Johannes Kepler had a lot around in the 1600s. But no one had ever looked at edges before or tried to count them. And so it was Euler that introduced the word achies for edges, and so that's that H. So this is the first appearance of Euler's formula. And further down the page of the letter, he takes a particular example, and he checks that it works for that. So I thought you might like to see that. And the formula also works for graphs drawn in the plane, as shown here. Here are the 5 regular solids, some of which we've already met. And if you draw their graphs, as I say, flatten them out, these are their graphs, and you can check Euler's formula for each of them. That works. And we can actually use Euler's formula to prove results about polyhedra. Now, this polyhedron here is called a truncated icosahedron, or some people call it a football. And as you can see, it's made up from pentagons and hexagons with just 3 faces meeting at each point. And more complicated examples of polyhedra made of pentagons and hexagons are the chemical molecules known as fullerenes or buckyballs. And here's one, is C60, which is essentially the same as this. But there are lots more complicated ones, all made with pentagons and hexagons. As I say, they're called fullerenes and buckyballs. And their name comes from Buckminster Fuller, the American architect who used the idea when constructing his geodesic domes that you can see below for various exhibitions and world fairs. And so what's interesting, they say that every maths lecture should have both a joke and a theorem, and you should be able to tell the difference between them. So here is a calculation, right? What's interesting is that for any of these polyhedra, where you've got pentagons and hexagons with 3 meeting at a point, there can be lots and lots of different numbers of hexagons, but there are always exactly 12 pentagons. And we can prove that using Euler's formula. So first of all, so I'm going to assume I've got a soccer ball with p pentagons and h hexagons. So the total number of faces is obviously p plus h. Now I'm going to count the edges around the faces. So there are p pentagons and 5 edges round, so that gives you 5p edges around the pentagons. There are h hexagons and 6 edges round, so you're going to get 6h edges round there. So the total number of edges is 5p plus 6h, it seems. Oh, but each edge has got 2 faces, so if you do this, you're going to count each edge twice, once for this face and once for this face. So in fact, you get 2e and not e. And similarly, you can count the 3 edges at each vertex, and you get a similar thing, 3v. Well, if you count the 3 edges, then each edge has got 2 ends, so you're going to get 2e again, and so you're going to get 5p plus 6h again. So you've got f, e, and v, and you can now substitute them into Euler's formula. So here's f. V is a third of this, is e, which is a half of this, plus 2. So there's that formula there. Well, fortunately, h plus 2h and 3h, they cancel. And that leaves an equation which you can solve to give p equals 12, so there must be exactly 12 pentagons. So we've proved the result. And you can also use Euler's formula in a similar way. I decided not to include it in this, but you can try it for yourself, to prove that there are exactly 5 regular solids, the ones I showed you earlier. So let's now move to our fourth problem, which I call the goodwill hunting problem. And in this film, if you saw it, you'll notice the janitor, played by Matt Damon, is walking down the corridor in the Massachusetts Institute of Technology, MIT, and he discovers a mathematics problem on the board. Now, the film describes this particular problem as an extremely difficult one, which the mathematicians at MIT had worked on for 2 years and finally managed to solve it. An exceedingly difficult problem in functional analysis. Well, don't worry about what functional analysis, but it's actually a very, very simple problem in graph theory to draw all the homomorphically irreducible trees with 10 vertices. And I'll explain what that means in a minute. But basically, that's an easy problem to solve. I've given it often to my students, and they all get it right first time, even if MIT professors take 2 years to do it. So let's look at trees. This is a tree, in case you've never seen these things before. And a tree is a graph that has no cycles. So below is a family tree, which is indeed a tree as long as there's no incest or anything like that. And then down below, here are some chemical trees. Now, these chemical trees have got 4 carbons, which form a carbon tree with 10 hydrogens around them. These are called alkanes or paraffins. So lots of paraphernalia here. So here are 2 different molecules with the formula C4H10. And the reason there are 2 different ones is because there are 2 trees with 4 vertices. Look at the carbons. You get this one and you get this one. And so you get these 2 different chemical molecules with the same formula but different structures. And they're called isomers. And you might say, well, how many isomers are there with say, 10 carbon atoms? Here are all the trees with 6 vertices. There are 6 of them. So how many trees have 10 vertices? How many trees have 100 vertices? These are mathematical problems which one might want to try and solve. And the particular one we're talking about, a tree is homeomorphically irreducible if it has no vertex of degree 2. Well, these vertices of degree, so that one's no good. This one's no good. This has got a vertex of degree 2. That one's no good. That one's no good. But these are okay. So there are two homeomorphically irreducible trees with 6 vertices, and there are a number with 10 vertices, and I'll leave that as an exercise for the reader. So you can solve the Matt Damon MIT problem yourself, I'm sure, without much difficulty. I should incidentally say that these counting problems were studied very much in the second half of the 19th century, in particular by 2 English mathematicians, Arthur Cayley and James Joseph Sylvester. They did a lot of work, very important pure mathematicians in this country. Sylvester also went, in fact, to America, and there's a whole chapter about him in this wonderful book here. But there's another result of Cayley which is quite interesting, which involved counting labeled trees. Now, although they're just 2 trees with 4 vertices, if you start labeling them, I mean, these are all the same tree, they're just a path, and these are all the other tree. But if you label them in different ways, then you can actually see that there are 16 different possibilities, 16 ways of labeling this tree. I mean, I've drawn them in different ways, but you can see that this is 2, 1, 3, 4. This is 1, 2, 4, 3, 3, 1, 2, 4, 1, 3, 2. There are all different ways of labeling it. And so how many ways can you label a tree with 4 vertices? The answer is 16. With 5 vertices, it's 125. 6 vertices, it's 1,296. Cayley came up with the formula that if there are n vertices, then the number of labeled trees is n to the n minus 2. So this is 4 squared, 5 cubed, 6 to the 4th, and so on. Unfortunately, Cayley proves his result in detail only in the case n equals 6, saying it's easy to see that proof works in general, which is not exactly a rigorous proof. And in fact, it took some years, in fact, not till 1918, when a German mathematician proved the result in general, and there are many proofs now. We're now moving on to our 5th problem, and here we wish to connect several towns or cities by links, which may be canals, railway lines, or air routes. But we wish the total connection cost to be as small as possible. So I want to choose some of these edges so that it remains linked up, but I want to do it in such a way that the total cost is as small as possible. So you certainly don't want to include a cycle, because if you include a cycle, you can take away any edge, and that automatically reduces the cost. So what we're looking for is a tree that goes through these 5 vertices. Well, we've just seen there are 125 possible trees. We don't want to go through them all. Let's look at a few. I mean, I could have taken this tree here. Well, that has cost 23. Here's a better one. This has got 21. This is even better. This has got 20. Is that the best we can do? It would be nice to have a method for finding the shortest tree. We don't want to have to go through all the possibilities. And in fact, there is a method, and it's called the greedy algorithm. Because at each stage, we are as greedy as we can be by choosing the smallest possible edge available. When I say the smallest possible edge available, I mean the smallest possible edge as long as it doesn't create a cycle. So the first thing we do is we look. We'll take AE. That's being greedy. That's cost 2. Now let's take EC. That's okay. But I can't now choose the edge 4 because that will create this cycle. So I ignore that one, and I choose the next one. That's this 5. Okay, so I've got this one, and this one. I can't now choose this one, which is 6, because that gives me a cycle. And I can't choose this one, which is 6, because that gives me this cycle. So I've got to choose the 7. So I've got this. Oh, and I've finished. So I've stopped. And that has total cost 17, which is better than any of the ones I had before. And the remarkable thing about the greedy algorithm, it always produces a tree with minimum possible cost. It may produce, if some of the costs are the same, it may produce different trees, but it always produces a solution to the problem, a tree with minimum cost. And if all these costs happen to be different, then in fact the answer is unique. There's just one solution. And this method for finding minimum cost trees was introduced by Czech mathematicians in the 1920s. The subject was revived in America in the 1950s, a couple of important papers by Kruskal. It's sometimes called Kruskal's algorithm, and someone called Prim. And in Prim's paper, here is his solution for the 48 coterminous states. That's, in other words, not Alaska and Hawaii, but the other 48 states. This is the minimum tree going through all of those capitals. Now, interestingly, that's a problem which has a complete solution. But there's another problem which sounds rather similar, but which is very different in practice. And this is the so-called traveling salesman problem, where you've got a traveling salesman who visits a number of cities selling graph theory books or something, and they want to visit the cities and return to the starting point, minimizing the total traveling cost. So this time we're not looking for a tree, we're looking for a Hamiltonian cycle, aren't we? So for example, for this, the same exact, we could go around the outside, that gives you 29. You can take this star pattern, that's also 29. This is 28, can you do any better? Well, I played around with it for a bit. This is the best one I could find. I think it's the optimum solution with total cost 26. But I had to do it by trial and error. There is, unlike the greedy algorithm problem, there is no simple algorithm known. And anyone who could find one would be worth millions of pounds, so I can encourage you to do that over supper. So unlike the other one, there's an easier to apply method, but for this one, there are heuristic methods which will give you fairly good solutions, fairly good approximations to the answer, but there is no complete answer. And in fact, it was some time before the problem for the 48 states was solved, and this apparently is the minimum cost for the capitals of the 48 states. So we come to our last problem now. In fact, two problems on the colouring of maps. In 1852, it was found that 4 colours are enough to colour the counties of England so that neighbouring counties are coloured differently. Okay, and so the question arose as to whether all maps can be so coloured. So here, for example, is a 4 colouring of the 48 American states. And on the left, you can see why you can't get away with better than 4 in general. Here you've got 4 neighbouring regions, so each of them must be different from the other 3, so you're going to need to have 4 colours there. And in fact, you might need 4 colours even if you haven't got 4 mutually neighbouring regions, as in this example here. The outside ring has got 5, so you can't alternate in colours. You're going to need 3 for the outside ring, and they're all going to have to be different from the middle one. So there's another one where you're going to need 4. And this example here occurs with Nevada. You've got the 5 states around forming a ring with Nevada in the middle. So, and the connection with graphs, by the way, I mean, here's a map of the states of Australia. Instead of colouring the states, you might want to colour the capitals and join them by edges when they're neighbouring. So you're really colouring, if you like, the vertices of a graph, whereas instead of having neighbouring states having different colours, here you've got joined vertices having different colours. So in fact, you can state it in the language of graphs, and when certain problems are solved, this is the language that graph theorists usually use. Well, the history of the 4-colour problem I've lectured on here before. You can probably find it on the website. So I'm not going to go through all that. I'm going to cut through to the end of it, where it was finally solved. Can you prove that all maps can be coloured with just 4 colours? This took 124 years to prove. And the argument is quite complicated. It's not deep, but it's difficult. And it was eventually solved in 1976 by Kenneth Appel and Wolfgang Harkun, who actually died just last October. You can see that they've used graphs rather than maps to solve it. Well, they actually managed to solve it with the aid of a computer by reducing the whole problem to just 1,936 different cases, which he had to analyze one at a time. In fact, they later managed to cut it down to a mere 1,482, but it was the first major problem in mathematics which needed the aid of a computer to solve it. And so although the proof was acclaimed, here's a Japanese newspaper. And incidentally, the University of Illinois, where they came from, they use this for their postal letters. So anyway, it was very, very popular. It was acclaimed, but it also caused much controversy by mathematicians who considered problems to be invalid if they can't be checked by hand. It was after it came, I wrote this book, Four Colours Suffice, on the history and solution of the problem, highly recommended. And in fact, when Appel and Harkun came to England to give lectures on their proof, I was able to celebrate with them. But I'd like to conclude with another related colouring problem, because colouring maps on a plane is the same thing as, essentially the same as colouring on a globe. I mean, you can think, here's a map on the plane. If you project it up, you get a map on the globe, and the other way around. So, I mean, here is a map, and you can colour the sea, and then you get a map on the globe. So if you can, so 4 colours. 4 is the number of colours you need to colour maps on a globe. So you can think of other surfaces. One of the simplest surfaces after a sphere is a torus, or bagel, if you like. Okay, and then you can have more holes in it, like a pretzel or whatever. Why you want to colour maps on pretzels, I'm not sure. But so now, one person who was involved with the history of the problem was proved by someone called Kemp in 1879, but the proof turned out to be fallacious. Hayward managed to find the error and prove the 5-colour theorem, that every map can be coloured with 5 colours, but he couldn't do 4. But he also generalised the problem: how many colours do you need to colour a map on a torus? And he gave the correct answer, 7. Here is a picture of a map with 7 countries on here, and here's a coloured version. So 7 is the magic number for a torus. For a double torus, one with 2 holes, the answer is actually 8. So how many do you need in general? And Hayward showed that if there are G holes in it, if G is the number of holes, then to get the number of, every map can be coloured with this number of colours. Looks a bit frightening. You take the number of holes, multiply it by 48, add 1, take the square root, add 7, divide by 2, and then take the integer part. And actually, that formula just comes out naturally from the mathematics. So, so he actually managed to show that every map can be coloured with that number, but he didn't actually show, apart from the torus, there are maps which actually need that number of colours. And to prove that was called the Hayward conjecture. And so I'd like to end up by telling you slightly, this is the last slide, that can you prove that, well, it was done by 2 gentlemen called Ringel and Youngs. It took a further 78 years to prove the Hayward conjecture. And it was done by Ringel, who was German, and Youngs, who was American, in California. And they completed the proof that on the surface of G holes, there are maps that need this number of colours. I'm not going to go through the proof. There are whole books on the subject. But their proof split into 12 separate cases. And 9 of them had been done by the middle of '67. And so Ringel, who I say was German, went to California on sabbatical for a year. The object of the sabbatical was to do the remaining 3 cases. And they succeeded. After about 6 months, they succeeded. So Ringel and Youngs had proved the Hayward conjecture. And to end with, I'd like to tell you a little story. There was great rejoicing in the graph theory world that the Hayward conjecture had finally been solved. And a couple of months later, Mrs. Ringle was driving up the California Expressway. And she was going a bit too fast. And she was stopped by a traffic cop who said, "Hey, you're going too fast. I want to see your driving license." So Mrs. Ringle, in fear and trembling, produced her driving license. And the traffic cop said, "Mrs. Ringle, Ringle, eh? Is your husband the one that solved the Hayward conjecture?" They're very, very well informed, the traffic cops in California. And Mrs. Ringle said yes. And it turned out that the traffic cop's son was in Professor Young's calculus class. And the result was that Mrs. Ringle got let off with a warning. So if you're looking for applications of graph theory, that's the best one I know. Thank you very much.
Knight's Tour problem that you get a semi-magic square when you add up all the things and all the entries in the grid. Do you get that for all solutions to Knight's Tour, and does it work for boards of higher dimension sizes?
It's an interesting question. Actually, I haven't heard it before. The semi-magic square we had was for 8 by 8 ones. It'd be interesting to know whether, I don't know the answer, whether it's been looked at very much for other sizes. Oh, by the way, 4 by 4 can't be done. 8 by 8 can be done. 10 by 10 can be done. I don't know about the magic square. 6 by 6, it's not clear, it's not obvious whether that can be done or not. Well, I mean, it is known, and I'm not going to tell you, so I will leave it to you to decide whether you can find a Knight's Tour on a 6 by 6 chessboard. But I don't know about magic squares on other sides.
Right at the end, you talked about the difference between necessary and sufficient conditions in the Ringle-Young's theorem. Right at the start of the talk, when talking about Tours and Euler and bridges of Königsberg, then you produced various other examples and said these can be done, these can't be done. I don't think you actually ever said why, if everything is an even number of vertices, it is actually a sufficient condition as well as a necessary one.
Yes, I skated over that. So did Euler. Euler said, you know, if you're going to trace it, then the number of vertices of odd degree is 0 or 2. And he said, and it is quite clear that by adding enough bridges or something, it is quite clear that if that condition is satisfied, then the problem can always be solved. And so Euler was not very rigorous. And in fact, the proof of the other way around, Euler was 1735 and wrote it up in 1736. The proof that it's necessary and sufficient wasn't until 1871. It was called Herholzer, I think, was walking up a corridor in Vienna, the University of Vienna, and he'd been working on such problems, and he happened to mention what he'd done and how he'd done it to a colleague of his, and then he died. But fortunately, his colleague had listened to what this person said, which doesn't usually happen, and he remembered enough to write up the paper. So it is necessary and sufficient. I did skate over it, so did Euler. I'm in good company. But the actual proof of the other way around was not done until over 130 years later.
And could I just ask one final question? What's your next book going to be about? Do you have a next book scheduled? Because we look forward to them.
Well, I'm on number 56 now, 57. Well, one of the next books is the one that I showed. There we are. We just handed this one in, so this might be the next one. I'm working on 4 at the moment. 2 I'm writing and 2 I'm editing.
And the other's not about graph theory, or always?
I think I gave a talk here. Well, I wrote a book on Oxford. I edited a book on Oxford civilian professors of geometry, which are the second oldest geometry professors in the country. Gresham College are the oldest, of course. And so I edited a book which came out last year on the civilian professors of geometry. But I felt there's also a need for the civilian professors of astronomy. Unfortunately, I don't know any astronomy, but I'm co-editing it with a colleague who happens to be the current civilian professor of astronomy. And so I think we're going to make quite a good team. We've just started on that.
Good heavens. Well, that's something to look forward to. I just wanted to say thank you very much on behalf of the audience online and in the room. And just to flag up, we do have one more, we have 2 more lectures left in the programme. Tomorrow we've got Sir Christopher Wren, Architect and Courtier, by our former Provost, Simon Thurley, which is going to be amazing, and you can probably watch it online if you can't get tickets in person. And finally, the Gray's Inn reading, which is on where we're at with freedom of expression, which promises to be very interesting too. So a very warm thank you to Professor Wilson.